In this video, we're going to continue on the solution to the method of images problem that we were working on in the previous video. In the previous video, we found that the potential V was equal to Q over 4 pi epsilon naught, big bracket, x squared plus y squared plus z minus d squared, square root 1 over minus x squared plus y squared plus z plus d squared, square root 1 over. For the setup where we had a positive charge Q, a distance d above an infinite conducting grounded plane, where we had this was the z axis. So this is the setup we had from the previous video, and this was the potential that we found. What we want to do in this video is find what is the induced surface charge, sigma, on this conducting plane. And we can find that by remembering that in chapter 2, we found that the induced surface charge on a conductor is equal to negative epsilon naught dV by dN, where V is the potential and N is the normal derivative of this potential at the surface. In this case, our n hat vector will point perpendicular to the plane in the z hat direction. Therefore, n hat is equal to z hat for this setup at z is equal to 0. And that means that our derivative d by dn is simply d by dz, again, at the surface, which is at z is equal to 0. So what we want to do in this video is find out what is sigma, and it's equal to minus epsilon naught dv by dz at the surface z is equal to 0. So now we want to use this equation, sigma is equal to negative epsilon naught dv by dz evaluated at z is equal to 0 in order to determine what is the induced surface charge on our infinite conducting grounded plane. We had the potential was V is equal to Q over 4 pi epsilon naught x squared plus y squared plus z minus d squared. And I'll write it this way, where we'll have the negative 1/2, indicating that the square root was on the bottom of the denominator. And this is subtracting minus x squared plus y squared plus z plus d squared. Again, the negative 1/2, indicating that it was a square root in the denominator. So we want to take the derivative of this equation with respect to z. So we'll do that. dv by dz is equal to q over 4 pi epsilon naught. Doesn't change because it's constant. We'll take the derivative here. We get negative 1/2 x squared plus y squared plus z minus d squared to the negative 3/2 times the chain rule, so we take the derivative of the inside as well. We get 2z minus d from the inside component. And this will all be subtracting off the derivative of this component here, which is negative 1/2 x squared plus y squared plus z plus d squared to the 3/2, negative 3/2 times 2z plus d, where this again is the chain rule derivative of the inside of this step here. Now we want to evaluate this at z is equal to 0. Z is equal to 0. So we get q 4 pi epsilon naught. We can cancel out some terms here. We have a 2 and a 2. Those will cancel. And we end up with negative x squared plus y squared plus 0. So we have negative d squared, negative 3/2. 0 minus d, so this will be just negative d here. And we get a negative and negative cancel to make a positive. The 2 will cancel with the 2 here. We have x squared plus y squared plus 0 plus d squared, so which is d squared. All of that to the negative 3/2. And then 0 plus d, left with just d here. One step further, we can go to simplify this. We end up with dv by dz is equal to q over 4 pi epsilon naught. Negative and negative will cancel, so we end up with d times x squared plus y squared plus d squared, since negative d squared is just d squared to the negative 3/2, plus d times x squared plus y squared plus d squared to the negative 3/2, And of course, these are the same terms. So our final dv by dz, evaluated at z is equal to 0, is 2q over 4 pi epsilon naught 1 over x squared plus y squared plus d squared to the 3/2. So now that we have found this derivative evaluated at z is equal to 0, we can plug it into this equation here on the left and find out what the total induced surface charge distribution will be for our infinite conducting plane. So we have that minus epsilon naught, and we'll plug this in, qd over 2 pi epsilon naught, 1 over x squared plus y squared plus d squared, so the 3/2. And we can see right away that these two epsilon naughts will cancel, and we'll end up with our final charge distribution in the xy plane. So sigma dependent on x and y is equal to qd with a minus sign over 2 pi 1 over x squared plus y squared plus d squared to the power of 3/2. And this is a charge distribution that is created on the infinite conducting plane due to the positive q, a distance d above that plane. So now that we have found out what is the charge distribution conducting on this infinite conducting plane, we can write that down as sigma, and it depends on x and y. And it's equal to minus qd over 2 pi 1 over x squared plus y squared plus d squared to the power of 3/2. Now this was the initial goal of this video, was to calculate this charge distribution. However, we can go one step further and calculate what is the total induced surface charge on our infinite conducting plane. And this is done by integrating the charge distribution function over the infinitesimal area element dA. And in this case, because we're using Cartesian coordinates, we can say that the sigma of x and y is integrated over dx dy, and this is a double integral. However, if we look at the function, we have x squared plus y squared to the power of 3/2 in the denominator. This will be a challenging integral to complete. So instead, we can rewrite this in terms of spherical coordinates, where we make the standard substitution r squared is equal to x squared plus y squared, and rewrite our area element as dA is dx by dy is equal to r dr d phi. So if we make this substitution, the integral will be easier to do in these spherical coordinates. This means that our function becomes minus q dd over 2 pi 1 over r squared plus d squared to the power of 3/2. So what we want to do is we want to integrate this function over this area element, and that will give us our total induced surface charge on this infinite conducting plane. So we write that q is equal to the integral of sigma of r and phi, double integral, r dr d phi. And our limits of integration will be 0 to 2 pi, 0 to infinity, all space. And we'll write our function in here, minus qd over 2 pi, 1 over r squared plus d squared to 3/2 r dr d phi. Now right away we can see that our function does not depend on phi, and so we can integrate that out right away, pull all the constants outside of the integral, and we have that minus qd over 2 pi integrating over d phi gives us 2 pi, and we have 0 to infinity r over r squared plus d squared to 3/2 dr. And the last step is to solve this integral. So we'll continue through and we'll find out what is the solution to this integral here. We'll use a standard substitution rule where we say that u will let u equal to r squared plus d squared, and then we'll say that du by dr will be 2r, which we can rearrange to become du over 2 is equal to r dr. And we'll substitute these two variables into here, so we get q is equal to, canceling the 2 pi's, minus q d. And then we have 0 to infinity of the r dr will give us du over 2, and we end up with 1 over u to the 3/2 in the denominator. So we can solve this integral here, which just says that q is equal to minus q d over 2 minus 2 over u to the 1/2, 0 to infinity. You can check this at home, but the integral of 1 over u to the 3/2 will be minus 2 over u to the 1/2. We'll substitute u back in as what it was before. Minus qd, we have a minus 2 here, over r squared plus d squared, where again our limits are 0 to infinity, and this is a square root, so we'll put it as the power of 1/2, and this is what we're trying to solve. So we'll have the negative and the negative cancel, the 2 and the 2 cancel, and we end up with that q is equal to q times d, 1 over infinity squared plus d squared minus 1 over 0 squared plus d squared, where both of these will be square rooted by solving this limits right here. So of course this will be 0 because of the infinity on the denominator, and 1 over the square root of d squared is simply d. So we're left with negative q d over d, where this negative sign comes in from here. The d's will cancel, and we'll end up with our total induced surface charge on the infinite conducting plane will be minus q. And this can be what we expected from before, because when we saw that we had the setup where we had a positive q and a negative q above and below the plane, it was as if we had an image of a negative charge projected at the same distance below the plane as we had an initial positive q above. What that means is that the total induced surface charge would be what we expect, negative q, on the plane. And then this is our final answer. To go along with this charge distribution, sigma is equal to minus q d over 2 pi 1 over x squared plus y squared plus d squared to the power of 3/2.